Hi and welcome to this section where we are going to look at the shift operator. But before we look at the shift operator, we would like to look at one or two examples, okay, about the central difference operator we looked at in the previous video. One, we would like to show that the second central difference operator at Fm is given as Fm plus 1 minus 2 Fm plus Fm minus 1. Then 2, we would also like to show that the third difference operator at that point is going to be equal to the third central difference operator, okay, is f of m. You forgive me if I sometimes say uncoordinated things, okay. However, I understand that you are very good students and you follow through, so you can be able to neglect my errors that I keep on making in here. And thank you for those who see the errors and put the notes in, add the comments or comment on them. I appreciate your help. So here we would like to look at here the solution. So for the purposes of time, we shall only do one, okay, because it is much shorter. I like doing the easy things and I leave the hard things for you. So we will do the short one. This one here will require some patience, okay, which I believe you have in plenty, but they follow the same idea, okay. It's just from the definition. Okay, look at this. So we know that the central difference operator here, second central difference operator, we can write it as the central difference operator on this operated on the central difference operator at Fm, okay. This is going to be the central difference operator. We know what is inside the brackets by definition. We saw last time is going to be f of m plus a half minus f of m minus 1/2, okay, which we can now again write, and then we say it is the central difference operator at that point minus the central difference operator at that point. So again, by definition, this is going to be f of m plus 1/2 plus 1/2 minus f of m plus 1/2 minus 1/2, okay, then minus f of m minus 1/2 plus 1/2 minus f of m minus 1/2 minus 1/2. So you see how easy it is. Then this is just going to be f of m plus 1 minus f of m, then minus f of m, then plus this negative and this negative give us a plus f of m minus 1, right? So what we have here is f of m plus 1 minus 2fm plus fm minus 1, okay. So this one here, it follows in a similar fashion, right? Okay. Great. So we move on to now what we call the shift operator. We would like to look at the shift operator, and it is denoted with the letter capital E, okay. Again, we go through the same things. For a given function, y is equals to f of x with the equidistant points x, and then the next one is x plus h, then x plus 2h, and so on up to x plus nh, right? This we define the operator E, the shift operator, okay, of f at the point x to be equal to f of x plus h. Okay, the shift e at f of x is simply going to be f of x plus h, i.e. e operates on f to give the next value, to give that what? The next value of the function. In other words, if we had the central, if we now have the shift operator, okay, of f at the point x plus h, it is simply going to be f of x plus h, which is going to be f of x plus 2h. Alright, and then generally the shift operator here, so we can say okay, yeah, it's just that f. So we can say that generally the shift operator, no, wait a minute, no, I think the shift operator at f of x plus h is simply going to be f of x plus h plus h, which is going to be f of x plus 2h. Okay, we can leave it at that. Maybe I was trying to confuse it with something different. So I think what I wanted is that now this is the second shift operator here, by definition can be given as the shift at that, okay, which is going to be given by the shift, and then we know by definition here this is f of x plus h, and then we know that this is now going to be f of x plus 2h. Okay, that is f of x plus h, which will be f of x plus 2h. Oh, I think this is what I wanted to write, that generally this is going to be given by f of x plus nh. Okay, the inverse shift operator is just the opposite. Okay, we shall now give us the value of the function before. Okay, so we can see that if we want this inverse shift operator, we can say that it is the inverse shift of f of x, which is the inverse shift of f of x minus h, and then the value before f of x minus h is simply going to be f of x minus h, which is f of x minus 2h. Okay, so now that we know something about the inverse shift, we have to go back and try to prove yes, this one here, which we said we would leave last time. So if we can start with 3, okay, 3, we want to show that the backward shift operator equals to the forward. Did I say backward shift operator? Oh no, now I'm confusing. See, I said the backward difference operator equals to the forward difference operator times the shift. Okay, so we say that for a given function f of x, okay, we are going to say that the backward difference operator at f of x, by definition, we say that it is f of x minus f of x minus h, okay, which is going to be equal to, which is the same as the forward difference operator of f at x minus h, because we know the forward difference of f at x minus h is simply f of x minus f of x minus h, right? So we know this is now forward, and then we know by definition that this is the inverse shift of f of x. Okay, so it similarly follows that therefore we can say that the backward is going to be equal to the forward times the shift, because we said we can cancel that. Okay, so for 4, I suppose you can also easily follow. You can also do what? Easily follow. What you will see in the notes, it's just they just use the same steps, and then they just use the definition of this and then transform the right hand side, and everything will follow. If there is anything you don't understand, you can please add it in the comment section. Thank you, and see you in the next video.